Okay, seems like everything is fine, so here we go. So we have a real system. We've made a model of the system, or we think conceptually in terms of a model. The model is finite dimensional, has a finite set of degrees of freedom, in fact has n degrees of freedom, and it's described by a mass, a stiffness matrix, a distribution of the loading, and a damping matrix to be discussed. Q are the coordinates, right? Our goal in this class really, in structural dynamics, we worry about the solution of this problem. That is, given the system and the loads, we want to solve for the Q's. In health monitoring, it's not the point. In health monitoring and identification, we are basically able to observe some of the cues. In other words, we are able to observe some of the vibrations and perhaps the load that is producing it. And what we want to do is to learn something about the system itself. At this point, it's worth keeping in mind that the eigenvalue problem is m, that m, times the mode shape is equal to, the stiffness matrix times the mode shape is equal to the mass matrix times the mode shape times the eigenvalue. That is, a mode shape has the property that when you multiply it times the stiffness and you multiply it times the mass, you really get the same thing except for a scalar. That is, to be explicit, if we had a stiffness matrix and 1, 2, 3 was a mode shape, that means that when we multiply it, we would find that the mass matrix times, if we multiply K times phi, we may find that the output is 10, 20, 30, right? Then we would say that 10, 20, 30 is m times phi, which is 1, 2, 3, times lambda, right? Now, if m times, in this case, we would see that, well, no, it's a little confusing the way I put it. Let me backtrack and just show it this way, so it's easier. Say m is the identity. So it's easier for me to explain. So if m is not the identity, I'd have to do 2 multiplications. But if m is the identity, then that means that m times phi is just phi. So that means that if you have k and you try phi was 1, 2, 3, right? And you found that m times 1, 2, 3, k times phi is equal to 10, 20, 30. M times 1, 2, 3 is equal to 1, 2, 3 times 10, right? So we would conclude that if we take the shape 1, 2, 3, when we multiply it times k, we find that it goes to 10, 20, 30. When we multiply it times n, it's 1, 2, 3. We see that to go from this to this, all we have to do is multiply times 10. So in that case, we conclude that 1, 2, 3 is a mode shape and that 10 is the associated eigenvalue, right? Okay. So the reason why I put that there, which is something that occupies us all the time in dynamics, is that in structural health monitoring and identification, we are going to observe some of the Q's and some of the U's, and our objective really is to find from there some of the phis and the lambdas, that is, some of the eigenvectors and the eigenvalues. Okay? Doesn't matter if it's not that clear to you right now, it'll get clearer as we go along. So the point that needs to be made in this lecture, so that you are at the same point of others, is that this equation is second order because it has two derivatives, and we would like to operate having only one derivative. So imagine that you say that x1 is q and that x2 is q dot. Then if you accept that, then you can write this equation as m x2 dot plus c dam times x2 plus k times x1 equals b2 times ut, right? So from there, it is a simple matter to know that x2 dot is equal to minus m to the minus 1k times x1 minus m to the minus 1 times c dam times x2 plus m to the minus 1 times b2 times ut. So all I've done there is just elementary algebra, right? I take this equation, I make this substitution, I write it again, I solve for x2 dot. Very simple algebra, right? You also recognize that x1 dot is x2, because if I take one derivative, I just get this, right? Therefore, you can write these two equations together like this. x1 dot, x2 dot equals, right? What is x1 dot, x2 dot equal to? Oh wow, I'm erasing it, but you have seen it. I shouldn't have erased it, but I needed the space. So it looks like this. x1 dot, and then here we're going to put x1 and x2. We're going to do a fill in the blank situation like this. So for example, x1 dot is x2, right? x1 dot is x2. So that means x1 dot is x2. So that's it. So the first partition of this system reads 0x1 plus x2 plus 0 is x1 dot. That's correct. The next equation, which I erased, reads minus m to the minus 1k times x1 minus m to the minus 1 c dam times x2 plus m to the minus 1 b2 times ut is equal to 0. And since this is a 0, I can put the ut outside. And this system that we get here is really where we want it to go from the very beginning. So what we have achieved right here is this. Imagine now that we call, say that we call x1 and x2. For simplicity, we just call it capital big X, right? Then you can see that this simply reads capital big X dot is equal. This matrix, we give it the name AC. So that's the matrix AC, and this vector is just capital X. We give a name to this matrix, which is BC, and then this is UT. So we have done the following. We have converted our original system of equations, which had two derivatives, to one that only has one derivative, right? Because this is just first derivative equals something. At the expense that the matrix A is twice the size, right? Because this is 2n by 2n, right? So we have, at the expense of doubling the number of equations, we have reduced the derivatives from 2 to 1. So this is A, and you should write it down. This is AC. It's a matrix that eventually you should know by heart. 0 identity minus m to the minus 1k minus m to the minus 1c. And this is the matrix BC that one also wants to know by heart, is 0 m to the minus 1 b2. Now that we have this, we say, okay, good. Now I want to solve this. Now, how can I solve this? Because, well, there are sophisticated ways to do it, or not sophisticated, there is an exact solution and so on. But for this class and for our purposes right now, it suffices to say, no, I want to be simple. So what's the simplest thing I can do? Well, all right, this seems logical. If I take this as an approximation for x dot, right? That makes sense, doesn't it? I take x at t plus delta t. In other words, let's assume that time is divided like this, and the distance between any 2 points is delta t. So that means the derivative at any point, if I have a function like this, right? The derivative here is approximately, this is t plus delta t. So the derivative here is approximately how much this changed divided by this, right? So how much this changed is x at t plus delta t, right? Minus x at t, and this right here is delta t, right? So that's that, and then I can write AC times x at t plus BC u at t, right? Cool. So that's easy. Now that we have that, we can say, okay, so let's say that we have x, and instead of using t plus delta t, it's shorter to write, or more conventional. We write k plus 1 to mean, you know, as you move along, this could be time station k, this is time station k plus 1, just like this is time station t, and this is t plus delta t, and so on, right? So we could say that time station at k plus 1 minus the time station k, multiply times delta t this side, we get AC times delta t times time station k plus BC times delta t times u at station k, right? And we then get what we wanted, where we were looking for, which is at this formula. X at k plus 1, putting that one on the right side, is the identity of order 2n plus AC times delta t, common factor of xk, plus BC times delta t times UK. Then we give this the name AD, and we give this the name BD, and we get that x at k plus 1 is equal to AD times x at k plus BD times u at k, right? Now that equation is really easy to solve, because if I know x at 10, then I can, with the load known, I can get x at 11, and with x at 11 I can get x at 12, and so on. So this is just a recurrence, which is simple algebra, and that you can just crank through it, right? Now, these formulas for AD and BD, that is that the way to go, when you go from C to D, it's called exactly C to D. That is, the process of going from the continuous model to the discrete model is called continuous to discrete, and in MATLAB there is a command called continuous to discrete that actually gives you A discrete and B discrete and so on, right? There are more sophisticated formulas to get the map, okay? So A continuous, B continuous, how they go to A discrete, B discrete, for example, right? This is what we would refer as D to C. I'm sorry, C to D. Backward process is D to C. So this is C to D. Now, this version that you have here, the formula that connects AC to AD and BC to BD, those are the simplest ones. But it is more common to go from AC and BC this way with either something called the zero order hold or the first order hold. It is simply meaning that you get a different formula because instead of idealizing the derivative using x at k plus 1 minus x at k, etc., the zero order hold and the first order hold are just based on assuming that instead of the input, which was varying, let's say like this, with time, if this were the time steps, in the zero order hold, we would replace the input by this. No, I'm sorry, not like that. It's just that these points were too close to being the same. It's not my best drawing. Let me make another one. That one is going to be confusing to you. Just want to make sure that the points are not at the same height so that the figure is clean. So if the input was like that, the zero order hold is simply take the value, keep it constant until you find the first one, the next one, then keep it constant until you find the next one, then keep it constant until you find the next one, then keep it constant until you find the next one, keep it constant until you find the next one. So if you replace the input by a stair like this, right? And you say, okay, I don't really have the black line, I have the red line. Then you get an exact formula for that input that varies like this. And that formula is what we would call the zero order hold. Actually, is the zero order hold for both of these things, right? So that gives you formulas. The first order hold simply assumes that you go as a straight line from point to point. So if you're here, you'd go like this, like this, like this. So basically you are replacing the input by a set of straight lines that connects the points that you're actually reading. These figures look really bad, okay, because the spacing is very far between points. But when we are working in reality, we are actually sampling these signals, 50 times, 100 times per second. So the points are very close, and the substitution that we are getting with a zero order hold or with a first order hold, it's really like we're going like this. Right? That would be a zero order hold, although I don't know, in the camera you can probably not tell anything. But it's like these guys are very small as you go from one to the next. So that would be a zero order hold, and a first order hold at that size you can probably not even see the difference from the actual line. My point at this stage is simply that you be aware that there are various levels of refinement on getting to AD and BD, and that the one that we just looked at is just the very, very simplest, right? Now, no matter how you get to AD, BD, the point which we will conclude is by looking at the recurrence, meaning if this is the state, let's see what happens if we say, what if I start with x0? So I will find that x1 is AD times x0 plus BD times u0, right? That makes sense? x1 is equal to AD x0 plus BD u0. Then x2 is AD x1 plus BD u1, right? But we already know what x1 is. Therefore, we say that x2 is equal to AD times this guy, which is AD times x0 plus BD times U0 plus BD times U1, right? And therefore, x2, it's really AD squared times x0 plus AD BD times U0 plus BD times U1, right? And then we would say that x3 is equal to AD times x2 plus BD times U2. And once again, doing the same thing, we already know what x2 is, so we would say that x3 is equal to AD, open parentheses, AD squared x0 plus AD BD U0 plus BD U1 plus what? Plus BD U2, right? Therefore, we find then that x3 is equal to AD cubed times x0 plus AD squared times BD times U0 plus AD times BD times U1 plus BD times U2, right? And now we don't have to go on anymore. We can generalize from here that xk is equal to AD to the k times x0, right? Plus, and then we can see how many terms are there after the first one. 1, 2, 3, when there were 3 x3. So this is going to be the summation from j equals 1 to k, right? Of what? There are various ways to do this, but I think this one is probably the most common. AD to the j minus 1. That means that when I start, I have AD to the 0 times BD. So AD to the 0, that means that this is going to be U at k minus j, right? So you can see that that works for all the terms over there. So we have just developed the recurrence that gives us the state at any k right away, right? It gives us the state at any k right away. It depends logically on the initial condition, right? And that initial condition gets multiplied by this. That's the effect of the initial condition on k. And this is the effect of what the loading adds to xk. Now, remember, don't lose sight. What is x? X is x1, x2. And what was x1 and x2? x1 was q and x2 was q dot. So basically what we're saying when we're looking at x at k, so when we're looking at x at k, what we're saying is that we are looking at the displacements at k and the velocities at k of the system, right? And this is how the displacements and the velocities in the system evolve. Now, we did just a little bit, maybe a few minutes more in the class last time, but I will repeat them tomorrow, so there's no need to put them here, and I will just call it done at this point. There is no new homework. There's no homework that has been assigned on this, so everything is okay. Hopefully, we'll have everything in order from the class, and we won't have to do this again. Closing it now.